we're going to turn to our fourth and last, but certainly not least, presenter. And you know, who knew which 4 talks would emerge today, but it's fun to me that they're all so completely different. So Yilan Xu is an associate professor in the Department of ACE, and she's going to be talking about some research that she's been doing on fracking.
Thank you for the introduction, Amy. I realized that this is an interesting time to talk about fracking now that we are less than a week away from the presidential election. But I want to make a full disclosure that this talk is based on 2 research projects that were conducted a few years ago. And one of the papers has been published in a journal and the other one is under review. Okay, so the purpose today is to introduce some research highlights from these 2 projects without necessarily get into super technical details. Okay, so what is fracking? So fracking is the technology that injects liquid at high pressure into rock formation to release oil or gas. It is a well stimulation technology to enhance productivity. You might have already known that, but you might be surprised that this technology is nothing new. It began in 1949 in the United States. What's new is the horizontal drilling. As you can see from this figure here, it increases the well's contact with the reservoir. So the combination of fracking and horizontal drilling makes it technologically and economically feasible to extract fossil fuels from shale formations. So then from this figure, you can see that wastewater is a byproduct of fracking, and you can see the trucks are involved in this process. So I have 2 research questions related to these 2 facts. The first one is, does fracking produce more wastewater? The other one is, does fracking related trucking cause more fatalities? The short answer to the first question is no. The short answer to the second question is yes. So in order to study wastewater, we pulled together a sample of onshore oil and gas wells from 17 states where they report the wastewater discharge month by month. From the data set, we don't know which wells apply fracking technique, but we do know which ones are horizontal and which ones are on shale formation. So in this research, we define those that are both horizontal and on shale formation as the unconventional oil and gas wells. And as I mentioned earlier, those are the ones that are more likely to use fracking. And then we also define all vertical wells as a conventional oil and gas well. So then from these first 2 figures, you can see that both the total volume of wastewater discharge of unconventional wells and the total number of unconventional wells have been growing over time in the past decades. But this is at the aggregate level. If you want to look at per well wastewater discharge, you will see that the per well wastewater discharge of unconventional wells exceeded that of conventional wells in 2014, and it has been higher since then. Although some people might feel compelled to conclude from this figure that unconventional wells produce more wastewater, this is not yet the whole picture. I want to bring to your attention that the share of new wells is always higher for unconventional wells than for conventional wells. And why does that matter? Because studies have shown that for unconventional wells, 20 to 50% of the first 10 years cumulative wastewater is generated in the initial 6 months. So separating those new wells from old wells is super important. So our goal of this study is to disentangle the lifespan effect and the cohort effect to understand the magnitude and the dynamics of the wastewater discharge of unconventional wells. Now, why does cohort matter? Because there has been consistent upgrades in fracking technology, which may actually make it more efficient. So let's look at what we found. We use an econometric model that compares the discharge month by month into their lifespan, controlling for resource type, the dominant product type, the energy production, and the local geology. Here I provide you 3 snapshots in time, 2008, 2011, and 2014. There are 3 findings here. The first one is that unconventional wells from monthly discharge is more front-loaded over time, as you can see, moving from left to the right. But within each figure, you can see that the monthly discharge actually decreases over lifespan. And it actually becomes lower than conventional well discharge at some point. Then next, we look at the cumulative wastewater discharge. By cumulative, I mean the discharge up to a point in a well's lifespan. So from these 3 figures, we can see that unconventional wells cumulative discharge becomes lower than a conventional well at some points. And the break-even point is delayed for more recent cohorts. By break-even point, I mean the time into the lifespan when an unconventional well has the same cumulative discharge as a conventional well. Okay. Here I also want to point out that the average lifespan of an oil or a gas well is 20 to 30 years. So the break-even point will be reached before the life ends. The last thing we look at is the wastewater to energy ratio. Here you see the negative gap between unconventional wells and conventional wells. And this can be interpreted as the efficiency advantage of conventional wells over, unconventional wells over conventional well. So from these 3 figures, we can see that unconventional wells are more efficient in the entire lifespan since day 1. And then we can also see that fracking has become more efficient over the time as the growing gap that can indicate when you move from left to the right. Okay, so here by more efficient, I mean more energy is produced for a given unit of discharge. So the 3 major takeaways from this wastewater study is that an unconventional well eventually discharges less cumulative wastewater than a conventional well. And it always produces more energy given 1 unit of wastewater discharge. And fracking technology is getting more efficient over time. All right, now build on this finding that fracking wells produce an intense amount of wastewater in its early lifespan. Next, we want to study whether trucks used to haul wastewater cause more fatal traffic crashes. Now, from this figure, you can see that the growth in fracking wells in North Dakota coincided with an increase in fatal crashes, especially the truck-involved crashes. If you look at other shale formation regions, the same thing is happening. But as an economist, we can say this is causal, right? Because we are looking at regional data. During the same period of time, there are also more migrants moving into the region, and there are also more commuters on the road because of the growing production in the region. And these factors are not necessarily directly related to wastewater hauling. So what we did was to do micro-level comparison across row segments so as to get around common shocks to the region, but also control for local differences. So for each row segment, we count the number of crashes in a given month, and we also count the number of wells at various production stages within the 6 miles of a row segment. So that we can then disentangle the effect of different production procedures. Here, by doing this comparison, we find that it's the post-fracking stages that matters a lot, which then is associated to the wastewater hauling. we found that one more post-fracking well within 6 miles of a road segment caused more fatal crashes by 8% and increased the accident severity by 7%. Okay, so the combined findings from these two studies call for an adaptive and dynamic regulatory system. This is because technology is improving. What used to be a problem at some point of in the history might become less of a problem or no longer a problem as the technology develops. And meanwhile, fracking also has a distinct production cycle. So a problem at some point of its life cycle will eventually disappear as the well matures. Another point we want to make is that sustainable infrastructure investment could be very critical. Local governments may want to develop a long-term and forward-looking perspective to account for technological improvements as well as the growth in the production scale. Thank you. Any questions?
That was right on time. Great job. Yeah, any questions anybody has? So while people think, I'm just curious. So this is great. When you hear people saying, we need to ban fracking, or no, it's going to save the world, given that you've done all this research, where do you come down on what our policies should be?
Right. Yeah. Okay. That's a great question. And our findings by no means imply that we should totally ban fracking. And actually, based on the finding list, a lot of things that the local government can do. Take the traffic paper, for example. Instead of totally banning fracking in the region, local government can think about regulating the timing of fracking across wells, right? So that they will not all happen at the same time to create traffic burden. And they can also redistribute the traffic loads over time, because one of our findings that I didn't have time to explain is that we find that most of the increases happen during the daytime rush hours. So there's a potential to reallocate the traffic loads over time. And then they can also create a system that resolve a truck lane, just in the idea of the HVO lane, right? Right. And then they can also create a traffic alert and warning system that can help people get oriented. So there's a lot of things that can be done based on the research findings, other than totally banning.
Yeah. That's great. So one last quick question: why is the break-even point delayed for more recent wells?
I think it's because it's getting, as we showed, that more upfront loaded. So the gap between between the unconventional well and conventional well is getting bigger and bigger for the initial 6 months. And that is resulting in the delay. But as I said, the lifespan averages from 20 to 30 years. So at some point, eventually it's going to result in a lower total wastewater discharge. And also, I want to highlight that unconventional wells tend to produce more energy at each point of time. So if you look at the energy efficiency, it's actually higher.
Great. Awesome.